All right, welcome back, guys. So in this part two video regarding differentials, we are going to do some math example. Hopefully, we can make sense of all these math symbols and formulas that I introduced in the previous video. So we just had to get the concept of differentials out of the way. So now we can try and understand this through an example. And then hopefully, from once we get the answer, I can re-explain what the answers stand for. So let's go ahead and do this. So this is asking for us to find dy for this given function x squared plus 3x, and we want to evaluate dy for part A and part B. Okay, so recall from the previous video, differentials, definitions, and formulas. Okay, so we define differential as df equal to f prime of x times dx, where dx is your increment delta x. Okay, so for this part A here, if dx is equal to 0.1, this is referring to the change in x from 2 to x equal to 2.1. So when you take the difference between those two value, your increment is going to be just 0.1. Okay, and we want to find the differential, which is the change in the y values, by applying this formula that we learned from the previous video. So let's go ahead and do this. So we know that first we need the derivative function. So if f of x is x squared plus 3x, then f prime of x is 2x plus 3. Okay, and we know that the given dx is 0.1 and x is 2, so we want to find the differential at the current level of x. Okay, okay, dy was just differential is equal to f prime of x times dx. F prime of x in this case is at the x value of 2, so we want to evaluate the derivative at x equal to 2. So that's just 2 times 2 plus 3, which is 7. Okay, so we plug that into the formula. Okay, so now dy is going to be f prime of 2 times dx, which is this case dx is going to be 0.1. Okay, so that's going to be f prime of 2 is going to be 7, we just found that, times 0.1, which is 0.7. So the differential is 0.7. Okay, so this is differential. It's 0.7, or the approximate change in y is around 0.7 if x goes from 2 to 2.1. Okay, and that's exactly what we just did there. Okay, this 0.7. Okay, this 0.7 is how much approximately change by the y value if x is increased by 0.1 from the position of 2. Okay, the second example, once we do the second example, is going to be a little more realistic. Well, not realistic, but still make a little more sense with this math problem here. So let me just go ahead and just explain furthermore what does this 0.7 represent here. Okay, all right. So if a function is this, okay, and if we go from x equal to 2 to x equal to 2.1, because that's what dx is, then, okay, or actually if we use the formula or the given equation, f of x equal to x squared plus 3x. Okay, and we get the exact change. Then we get the exact change in y. Okay, so here's the exact change in y. It is f of x plus h minus f of x, and then f of x plus h in this case is f of 2.1, because h is the change from x from 2 to 2.1, or dx in this case is 0.1, minus f of 2. So if the formula is x squared plus 3x, f of 2.1 is 2.1 squared plus 3 times 2.1 minus 2 squared plus 3 times 2. Okay, if we do the math correctly, this should give us 10.71, and this should give us 10, so that gives us 0.71. So look at this answer here. So the exact change in y is 0.71, and look at our approximate answer, which is the differential, which is dy here. That's the differential. This is the exact. Okay, not much difference in terms of the how close our estimation is. So that's pretty much it, right? That's what we just did there to demonstrate what the differential means. It's just what the formula we use to estimate how much change in the y or the vertical distance if we have some change in the increment. Now what we're going to do next is use that differential formula to solve an application. And hopefully by the end of this application problem here, this word problem, it makes a little more sense, or at least you start feel like, okay, you can process what differential is regarding an application. Okay. All right. So a company manufactures and sells X transitor radios per week. If the weekly cost and revenue equation are following. Okay. So we got the cost equation for manufacture and sell transitor radios per week. So this is the cost. This is the revenue. Right. So this is cost functions, and this is revenue. And X is the number of radios, transitor radios, right? Manufacture and sell, where we go from 0 to 8,000 there. It says here, use differentials formula to approximate the change in revenue and profit if production is increased from 6,000 to 610. Okay. So let's do this. Let's do the cost first. Okay. So if our X is the number of radios manufactured and sell per week, then our delta X or dx, okay, or dx is dx or delta X, okay, is equal to the current level 6,000. No, is the new level 6,010 minus 6,000. So increments is 10 radios per week. Okay, so that's gonna be our increment. Okay, that's delta X. The differential formula is change in cost, delta C. Okay, or delta C. So this can be approximated by the function derivative, which is C prime of X times delta X. Okay, so this is the change in cost per week. Okay, if production increase by 10 per week. Okay, and then this part is going to be confusing. This C prime of X here, we haven't quite get to the formula of what the business term for derivative of a cost function yet. So right now we can say, okay, if that's the derivative of cost function, so this tell us the cost per unit per radio at the current level production. Okay, and that current level production is X equal to 6,000. So at 6,000, C prime of 6,000 will tell us how much the cost is increasing by per radio. Okay, so now we got that out of the way. So let's go ahead and find C prime of X. So if C of X is 5,000 plus 2, then C prime of X is going to be just 2, because if C of X is 5,000 plus 2x, then let me just write that fully. Right, C of X 5,000 plus 2x, so C prime of X is just 2, using the rule of derivative, power rule. And then we got delta X already, which is 10. So now we can say the change in cost. So we say the change in cost can be approximated by C prime at the 6,000 current level plus, okay, not plus, times delta x, but delta x in this case is 10, and then c prime 6000 is going to be just 2. Okay, so what this saying that no matter what this saying that the so this c prime of 6000 right here, so which is equal to 2, so c prime of 6000 equal to 2. So this saying that this is how much the cost. So this is cost increasing at $2 per radio at the current level of 6,000 radio produced per week. Okay. All right, now let's finish the problem here. So delta C, or the change in the cost, is approximately $20. Okay. Okay, so let's make sense of this. Okay. If production increase from 6,000 radios to 6,010 radios per week, then the approximate change in cost is around $20 per week. Okay. So now we may ask, why would we want to approximate the change in cost if we already know the equation for the cost, which is here, and we just plug in the two numbers and then figure out the cost that way, the change in cost that way? Well, that is indeed a good question. Now, the problem with that is in real life, chances are we don't have the exact math formula to calculate every dime and penny of the cost a certain unit is in production. So we don't have the actual precise formula, so we can only estimate it. So this derivative here, this here, usually can be computed at that current level of production by tally up all the costs. So that can be done. But this is not quite realistic, because if you have a really large company that in charge of a lot of stores or just franchising, it's not easy to have one single formula that calculate all the costs. I mean, it could probably be an approximate formula. So we don't have that. So not okay. So the using differential to approximate the cost become very useful. Okay. And I'm gonna leave you guys to do the change revenue on your own.